We're going to take a look at work, and what you need to realize is that work done is energy transferred. So these are equitable quantities, and they're often used as synonyms of one another. Work is measured in joules and energy transferred is measured in joules. It's a scalar quantity, in other words, it does not have a direction. Force times displacement, what's really important is that the displacement must be in the same direction as the force, because of the fact that you've got to eliminate the direction as a component or anything at all. So you make sure that both of those are in the same direction. What is a joule? A joule is a Newton times a meter. Force is measured in newtons. Displacement is measured in meters. What is a Newton really? Well, newtons measure force, and force is mass times acceleration. So a Newton is really a kilogram meter per second squared. So that's what we put in instead of Newton. Then the meter stays there. Then meters times meters is meters squared. So the base units for a joule is a kilogram meter squared per second squared. 1 joule of work is done when a force of 1 Newton acts through a displacement of 1 meter in the direction of the force. Very important that it has to be in the direction of the force. So this is really very challenging. Work done is equal to force times displacement, and force is 1 Newton and displacement is 1 meter, and 1 times 1 equals 1. And so it's newtons, meters becomes joules. In order for work to be done, the force has to be acting in the same direction as the movement. That's what I've just been saying a minute ago. This is not the case. You have to calculate the component of the force that is in the same direction as the movement. So if two things were acting in perpendicular to each other, there would be absolutely no work done at all. So for example, let us say that I had a little piece of metal on a string, and I'm standing in the middle here, and I am spinning that piece of metal around and around my head. Alright, so it's spinning. Let's think about the forces here. There's a force over here of tension. Alright, so the tension is this weight piece over here is holding a tension in the rope. This is also, it has a weight going down into the ground. Okay, so from here it kind of goes into the page. But what is the direction of motion? The direction of motion is a tangent to the curve at any time. That tangent to the curve is perpendicular to that force, and the tangent to the curve is perpendicular to weight. So you can say that no work is done in the horizontal direction at all in terms of the spinning little piece of metal on a string. So no work is done if you are not in the same direction. In other words, especially if you are perpendicular. If you are partially in the same direction, you can work out a component of the force using sine and cos. Energy is equal to force times displacement. Why? Because energy is work done. Energy is the ability to do work, and it is measured in joules. And you've got lots of different types of energy. You've got heat energy and light energy and electrical energy and potential energy and nuclear energy and kinetic energy and sound energy and thermal energy, and so it goes on. And there will always be a transfer of energy from one to another. The two we're going to focus on, though, are kinetic energy, which is the energy possessed by a moving object, and it is equal to a half mv squared. The v is velocity, and that means that there must be movement. Half the mass times the square of the velocity gives me kinetic energy. And let's just look at our units. Kinetic energy is half mv squared. What's the unit of mass? Kilograms. Speed, meters per second squared. Meters per second again. Meters squared per second squared, and don't forget that is a joule from earlier. So if I was asked to determine the kinetic energy of a 5,000 kilogram truck moving at 40 kilometers per hour, the first thing that I'm going to have to do is change that kilometers per hour into meters per second. And how do I do that? I say 40 kilometers divided by 1 hour is the same as 40,000 meters. What is 1 hour? 3,600 seconds. So I get 11,11 meters per second, more than Nelson. Then I am going to say 5,000, substituting in a half m v and squared, and I get 308,641,98 joules. So that is the kinetic energy. The other type of energy we're going to focus on is something called gravitational potential energy, and that is the energy possessed as a result of a body's position, really above the ground, because it's got to do with gravity. And it is measured as mgh, mass times gravitational acceleration times the perpendicular height above the ground. It's important that it's the perpendicular height above the ground. So in other words, if I've gone up a slope like that, it is not the length of the slope, which let's say is 10 meters, it is the height over here. And if that was 30 degrees, I would need to use sine in order to establish what that was. Anyway, let's look at our units again for potential energy. Potential energy is mass, kilograms. G is gravitational acceleration, meters per second squared. Height is measured in meters. And again, I come out at the beautiful unit of joules. Let's calculate this. We've got Fred, and he's running to the top of a flight of stairs. There's 7 steps. Each one is 40 centimeters horizontally. We're not interested in his horizontal motion. Why? Because the force is his weight, and that is acting downwards. So we are only interested in the bits that go upwards, and the bits that go upwards are 7 times 50 centimeters, which is 3.5 meters going up. Mass of Fred is 58 kilograms. The gravitational acceleration, I've left this as 10, it should be 9,8, and therefore we're going to have a fractionally different answer. So I land up with 1,989,4 joules rather than that, because of 9,8. What's important here is that we are only interested in the distances that are in the same direction as the force that is being exerted, and the force that is being exerted is weight, which is mass times gravitational acceleration.